All right, so question one, a set containing three elements, and they can be any elements that you want. So A, comma, B, comma, triangle. There's a set containing three elements. That's perfectly fine. So everybody got a set for three elements. Describe the elements of the set of all x such that x is bigger than 5. So some people did this. Right, like that. And what other ways? All numbers greater than 5. The open interval 5 comma infinity, using open interval notation. But there's also 6, 7, 8, dot, dot, dot. These are very different sets. All right. This set contains an infinite number of real numbers, 5.1, 5.2, 107, 13,000, and 5.2. Those are all contained in this set. This set also contains an infinite number of elements, but there are 6, 7, 8, 9, 10, and so on, right? Different sets because the universe makes a difference. If we just say the set of all x such that x is bigger than 5, we don't know, does that include the number 5.5. Well, if that's not part of the universe, it doesn't include it. Or as one group said, maybe we're picking from the universe a prime number, so this set would contain the numbers 7, 11, 13, 17, 19, and so on. So the universe definitely makes a difference. The collection of universe from which x can be chosen will affect what that set looks like. So a more proper way to define this set might have been the set of all x contained in Z such that x is bigger than 5, or the set of all x contained in the real numbers, or whatever we had in mind. So there's a potential ambiguity if we just say this. Now if it's clear from context, if we're doing a unit on integers and sets of integers, then it may be clear that that's an integer set. So in 3 it says describe the set of integers between 3 and 7 using the above notation. So that's going to be a set containing what, 4, 5, and 6. And using this interval builder notation, we could say the set of all x such that x is bigger than, I forgot the question already. And it doesn't say whether to include 3 or 7 or not. That's another ambiguity. Integers between 3 and 7, does it include 3 and 7? I don't know. So if we decide it doesn't, this is a set of all x such that x is bigger than 3 and x is less than 7. Or you might shorthand this like a 3 is less than x is less than 7. And that's pretty safe. Or if you believe that between 3 and 7 includes 3 and 7, it could be less than or equal. And if you ever see something like this on a test and you don't know if it includes the ends or if it's integers or reals or something like that, that's where you come up and you ask, right? Or you raise your hand and say, hey, this is a bad question. Clarify what you mean. And I'll try to clarify unless it's part of the question. All right, describe the following intervals of real numbers. So here again, we're told what the universe is. It's a set of real numbers. And the first one is open interval 1 comma 3. And so this is the set of all x contained in the reals such that x is bigger than 1 and x is strictly less than 3. And if you wanted to draw this on a number line, it's basically everything not including 1 and 3, but all that stuff in between. And the others work the same way. The open interval, the half open interval 2 comma 4. So it's everything bigger than 2, but everything less than or equal to 4, and all the stuff in between. So usually for these kinds of things we can draw a circle if we say don't actually color in that number, or we can draw a big dot to say it includes that number. All right, good on those. All right, so question 5, describe a set S containing two other sets. And I saw a lot of different ways of doing this. Basically, define some sets. So A might be the set 1, 2, and B might be the set, 4, 6, and -11. And if I want a set S that contains two sets, I could just say S equals the set containing A and B. Which is also the same thing as a set containing the set 1, 2 and the set 4, 6, and -11. But one thing to note, this is not the same thing as the set 1, 2, 4, 6, -11. Why are they not the same thing? How could you convince someone in a court of law that this is not the same thing as that? It's shown as one set instead of separate sets.
Under your definition, the bottom there says 1 is an element of that set.
Yeah, right?
And if it's going to be a subset of S, 1 has to be an element of S.
Yeah, so for two sets to be equal, they have to have the same elements. Well, this set contains 1. Does this set contain 1? It contains an A and a B. It doesn't contain a 1. A contains a 1, but that's totally unrelated, right? So a lot of set theory is about sort of tuning down your brain so that you don't think too deeply, which is kind of weird, right? Very, very literal interpretation of the definition. These sets are equal if everything in here is contained in here. Well, S contains an element A. Is there an A in here? No, 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 nope. Not contained in here. They can't be the same set. Right? And we want to say, yeah, but this makes up A, so it contains the elements of A, right? But we're thinking too deeply at that point. So very literal definition. And a lot of what we're doing in this course is going to be working with definitions. And when someone gives you a definition, right, you live and die by that, right? You can use that, and if that means that my answer is 0, hey, I can write down a 0 and I'm done. Okay? Doesn't matter if it leads us to something ludicrous. If we adhere to the definitions and we apply logic, our answer is going to be correct. And we'll have a lot of fun with that when we start talking about propositional logic. All right, so there's lots of examples you could have done here. We could have done S equals the set of integers and the set of reals. Or we could do S equals the set of integers and the empty set. Can the empty set be a member of a set? Yeah, it's a thing. Sets are collections of things. Can we do that? Can we say S is a set containing the element S? If S is just a collection of things, S is a thing, technically we can do this. But this is a danger point. We'll play with this on Friday also. This is going to lead us to something called Russell's paradox. Turn of the century, 1900s, people were playing around with set theory, and if you do this, you can get yourself backed into a really, really interesting corner. And it's a corner called Russell's paradox, and we'll do some exercises and play with that. It'll be a lot of fun. But this is a peculiar thing, okay? But other than this particular case, right, S could be a collection of anything. So yeah, that's a fine collection of two sets. Even if one of them is the empty set, that's fine. All right, ready to keep going? All right, so another worksheet on subsets. So back to the board. And I'll put this up on the overhead, and let's play with some subset exercises. And then we'll take a break, and then we'll start talking about set operations. And that will set you for homework. Yeah, you can erase what you got. So let's run through these and then we'll take a short break. So define a set containing 3 elements. So everybody did that, and it can be, again, whatever your favorite set of 3 elements are. So I'll just go A, B, C, but there are other possibilities. Find a subset of S. Use the definition to prove to yourself that you really constructed a subset. Well, here's a subset, A. And how do we know that that's actually a subset? Well, what's the definition say? A is a subset of B means if X is in A, then X is in B. So if X is in here, if X is an element of this, it must be an element of this. Well, there's only one element of this, which is the letter A, and that is a letter contained in that set. So that's enough to prove using the definition that this small singleton set is a subset of that original set. Right? And it's obvious this is a subset, everything in here is in there, but think about the definition, right? And try to understand the connection between what's obvious in your mind and those definitions. Because another part of what we're doing in here is we're going to be trying to do very formal proofs. And the trick of one of the tricks of formal proofs is we'll see something and it's obvious to us, right? But how do we turn that into a formal demonstration of what's obvious to us? And the more obvious it is to us, the harder it is to do that formal demonstration. For example, if it's sunny, then I am going to play tennis this afternoon. Okay, suppose I tell you that statement is true, and then I also tell you that, hey, it is sunny. You can conclude, I'm going to play tennis this afternoon. But how do you prove that? I mean, it's obvious. You just said if it's sunny, you're going to play tennis, and it's sunny out, so you're going to go play tennis. But how do you actually turn that into a formal proof? That's what we're going to study when we do propositional calculus. Okay, so we want to always come back to the definitions and be thinking about what's going on under the hood. So that's kind of what question 2 is about. Find a second subset of S. Well, I don't know. Here's another subset. How about B, comma, C? So everybody found that. So what's the largest subset of S? The subset containing the most elements. And we already noted before that that everything is a subset of itself, right? B is always a subset of B, and that's the largest possible subset. Right? There can't be a bigger subset, because if we had a bigger subset, it would have to contain something other than A, B, or C, and we know it wouldn't be in the set on the right, because this only contains A, B, and C. So this has got to be the biggest subset, and it's got 3 elements. And then the smallest subset, that's kind of a trick, that's always the empty set. And we know that just because we remember the empty set is a subset, and this is the smallest set possible. It has nothing in it. The only way it could be smaller is if it had less than nothing in it. And we don't have those things. Okay, find all the subsets. So this is a trial and error kind of thing. But this group up here was doing it in an interesting way. They wrote out the elements in a particular orientation, like this. And then they wrote, yeah, like a truth table. Right, where they're including or not including each element. And 1, 2, 3, 4, 5, 6, 7, 8 subsets. And the group on the end here cracked the secret code. Why are there exactly 8 subsets when you have 3 elements? It's 2 to the 3rd. And why is it 2 to the 3rd? Because each set we write we can describe as follows. Is the letter A contained in the set? Either yes or no. There's 2 possibilities. Is the letter B contained in the set? Yes or no. There's 2 possibilities. Is the letter C contained in the set? Yes or no. We could write a 3-bit binary number corresponding to each of these sets, where 1 means that A is contained in the set, right? The first digit 1 means A is contained, and a 0 means A is not contained. And the second digit will be a 1 if B is in the set, and a 0 if B is not. And so this would correspond to the binary numbers 111, 110, 101, 100, and so on. And there's this one-to-one correspondence between these 3-bit binary numbers and these subsets of a set of 3 elements. And any 3-bit number corresponds to a set, and any set corresponds to a 3-bit number. So how many subsets are there? How many 3-bit numbers are there? And we may know from Engineering 250 that if you have 3 bits, you have a total of 2 to the 3rd possible numbers, which if we're counting in binary go from 0 to 7. And that's a general thing. It doesn't matter what the elements of the set are. It could have been the numbers 4, 6, and 12, right? We still have 8 subsets. And so how many subsets of the empty set are there? Well, a subset has to contain elements from here, and there are no elements in here, so the only subset is the empty set itself. So there's exactly one subset of the empty set, and if we apply our formula, the empty set contains 0 elements, the number of subsets should be 2 to the 0, which is 1. So that's a good formula for how many subsets we have. But only if we have a finite set. If we have an infinite set, like the set of all integers, contains an infinite number of things, the number of subsets would be something bizarre, like 2 to the infinity question mark, and that doesn't have any meaning. But certainly it's an infinite number of subsets, right? And we could prove that pretty easily, because subsets of Z would include the singleton set containing 1, that's a subset of Z. The singleton set containing 2 is another subset. The singleton set containing 3 is another subset. And I can certainly make an infinite number of these subsets, just the singleton set containing any integer. So right there, just with that family of subsets, I've got an infinite number. But then there's also more subsets than that. Friday we're going to talk about how many. We're going to talk about things like 2 to the infinity, and if all infinities are the same. All right, questions on that? So let's take a 5-minute break. Let's come back at 1:30 and let's start talking about set operations that you're going to need to know for the homework. And I will glance at the homework so I know what to talk about. All right, so let's talk about set operations. So one thing we love to do in mathematics is make new things out of old things, make big things out of small things, right? And one thing we can do is with sets, we can put sets together and create new sets. And so there's a series of operations. And let me just give you some examples first, and then we'll formalize it. So suppose A is the set 1, 2, 3, and B is the set 4, 6. We can describe the union of these sets, and it's what you get by putting them together. Okay, so in this case it would be 1, 2, 3, 4, 6. And this is A union B, or the union of A and B. And we can have a set X equals the set containing 1, 2, 3, and the set Y is a set containing 1, 3, 5. And the union of X and Y would be the set we get by just putting these two sets together. It would not be the set 1, 2, 3, 1, 3, 5. Okay, remember we can't write a set that lists an element more than once. It would simply be the set 1, 2, 3, 5. So again, back to definitions. This union, X union Y, is the set containing all elements that are in A or B. So it's got to have a 1 and a 2 and a 3. It's got to have a 1. It's got to have a 3. It's got to have a 5. So it's the set 1, 2, 3, 5. Okay, so not 1, 2, 3, 1, 3, 5. All right, we can define an intersection. X intersect Y. Either X intersect Y or the intersection of X and Y. And that's the set of all things that are in both x and y. So x and y both contain a 1, and they both contain a 3. So that's what the intersection is. So what's the intersection of A and B? Elements that are in both. Well, there are no elements that are in both. So that is going to be the empty set. All right, we can also talk about subtraction. A take away B. And we can call this A minus B, or the complement of B in A. So let's do it with x and y first. X take away y, or x minus y. It means start with the set x and throw away anything that you find in y. Start with x, throw away anything that's in y. Okay, so we start with 1, 2, 3. And we're going to toss out anything that's contained in y. Well, the number 1 is contained in y, so that gets tossed out. The number 3 is contained in y, so that gets tossed out. The number 5 is contained in y. If that was in here, it would get tossed out, but it's not in there. We're left with just the number 2, and the number 2 is not contained in y. So this is just the set containing the number 2. So up here, what is A take away B, or A minus B, or the complement of B in A? It's just going to be 1, 2, 3, because we're going to start with the things in A, and then throw away anything that's also in B. Well, that's not in B, that's not in B, that's not in B, so there's nothing to throw away. So it just turns out to be equal to A. So those are our three fundamental set operations: union, intersection, and complement, or subtraction. And from examples, it's usually pretty clear what's going on, and we can generalize that. But let's write this formally. A union B equals the set of all elements x such that x is in A or x is in B. And remember, this colon or this vertical pipe reads as such that. So what do you think A intersect B might look like formally, like this? Set of all x such that x is in A and x is in B. Now, I haven't specified what x comes from. There's got to be some notion of a universe, but I'm assuming that that's understood, right? And it depends what universe we're working in, but it's presumably a universe that contains at least all the stuff that's in A and B, so that this makes sense. So the union is a set of things that are in A or B. The intersection is a set of things that are in A and B. All right, the complement, A minus B, is the set of all things such that x is in A and x is not in B. And I want to expand the notion of complement a few ways. One is sometimes we'll write A minus B, but a more common notation is A backslash B. And that means A take away B, or A minus B. All right, we know this funny symbol means the empty set. What's the extreme opposite of the empty set? The empty set is a set containing nothing. What's the other endpoint of some sort of spectrum?
The universe.
Yeah, the set containing everything, right? And we call that the universal set. And that's the set containing everything. Everything in the universe. This should be a fancy looking script U, but I'm not very good at drawing fancy script U's. So, I don't know. Draw your favorite fancy script U. Make that the universe. So there's a particular complement we like to talk about sometimes, which is the universe take away B, or the universe minus B. The complement of a set in the universe of all possible things. And this would be the set of all x, such that x belongs to the universe and x is not in B. Well, if U is the universal set that contains everything, the set of all x such that x is contained in the universe, that doesn't really mean anything. That doesn't restrict anything, because x is always contained in the universe. That's what the universe is. So the universe take away B is really just the set of all x such that x is not an element of B. And we have a special name for this. This is called the complement of B. And sometimes you'll see that written as B with a little c on top of it. Again, different notations and different sources. The book uses this one a fair amount. So B with a little c, that's the complement. And we can formalize that. The complement of B is the set of all x such that x is not contained in B. Okay, good on those four ideas: union, intersection, complement, and subtraction. And we're not going to deal with this one a whole lot today. It's really just union, intersection, and complement. And you've seen these before probably in some form, so this may not be entirely new to you. But let's look at properties of these. Well, here's one useful property. If we take A union B, we get exactly the same thing as if we take B union A. How do we know that? A union B is a set of x such that x is in A or x is in B. B union A would be the set of x such that x is in B or x is in A. It's exactly the same thing. We just phrased it in a different order. So this is always true. Anybody know what this property is called? Besides you. Do you know what this is called? Commutativity, right? We can say that unions are commutative. And not surprisingly, that also works for intersections. Again, you can go to the definition. A intersect B means a set of x that are in A and in B. B intersect A is a set of x that are in B and in A. It's exactly the same set. We can do multiple unions in any order we want. If we take B union C and then we union that with A, we will get the same set as if we take A union B and then union that with C. Anybody know what this property is called? Associativity, good. And it also works for intersections. And they won't list the union intersection pair for all of these, but usually if it works for one, it's going to work for the other sort of automatically. What do you think A union A is equal to? That's just the set of things that are in A or that are in A. That's just A. That's also the intersection of A with itself, the set of things that are in A and are also in A, just the set of things in A. What about A union the empty set?
A.
That's just A, a set of things that are in A or that are in the empty set. Well, there's nothing in the empty set, so that's just A. What about A intersect the empty set?
Empty set.
All right, because it's got to be in A, but it's also got to be in the empty set, and there's nothing in there. What about A union the universe? Things that are in A or in the entire universe, that's just going to be the universe. How about A intersect the universe? Things that are in A and also in the universe, that's just the set A. Let me know if this starts to feel familiar in any way, shape, or form. We also have this fact. A union, the intersection of B and C, is equal to A union B intersected with A union C. This is something we can call distribution. A union B, complement of the whole thing, is equal to the intersection of A complement and B complement. That look familiar to anybody? What have you seen before that might look like this? Yeah. Engineering 250. Remember something like this? Let me write it a little differently. Let me write the complement by putting a bar on top of something. Have you seen this before? What's that called? De Morgan's theorem. Excellent. De Morgan's theorem works for sets. So does distribution, associativity, commutativity, adjacency, all these things that we learned in 250, things that we touched on briefly in 120, they all apply to set theory. We'll see how to prove some of these things on Friday. We're going to prove them with something called a membership table, which is going to look suspiciously like a truth table from 250. It's exactly the same thing, actually. It's not a truth table, it's a membership table. All right, let me talk about one other way we can combine sets, and this will be the last one that you need for your homework. Suppose A equals the set 1, 2, and B equals the set G and W. We can define what's called a Cartesian product of these two sets. Cartesian product of two sets is a third set. And the elements of this third set are what we call tuples, an ordered pair. So each element of this set is going to be two things in parentheses separated by a comma. And this is not a set because I'm using parentheses instead of curly brackets. This is like a coordinate on a graph. It's two things. There's a first thing and a second thing, and they're separated by a comma, and they're in parentheses. And in order to be a tuple in this Cartesian product, the first thing in here has to come from A, and the second thing has to come from B. So all the elements of this set are the following: 1 comma G, 1 comma W, 2 comma G, 2 comma W. And that's what the Cartesian product looks like. 1G, 1W, 2G, 2W. And these are just things, happen to be called tuples. So this cross product, this Cartesian product, contains 4 things. Each is a tuple where the first element comes from A and the second element comes from B in any possible combination. All right, and that concept you'll need for one of the homework questions. So let's take a look at the homework. So section 1.1, questions 2 and 4. We'll flash the important screen because we're going over the homework now. All right, so homework 1.1, question 2 lists all the elements of the following sets. The set of 1 over n such that n is 3, 4, 5, or 6. So presumably we're working over real numbers or something here. So that's a set that's going to have 4 elements in it. The set of alpha contained in the alphabet, that's the English alphabet, I guess, such that A precedes F. Right? There aren't a whole lot of tricks in here, right? So don't look for the trickier meaning. The set of all negative k such that k is contained in this letter P, which I like to believe they describe somewhere as being the set of positive numbers.
Yeah.
Do they? Okay, we use a symbol P instead of writing 1, 2, 3, dot, dot, dot. All right, so the set of negative k such that k is contained in P. So let k be some element of the positives. Your set contains negative k. So think about what the whole set F of elements looks like. The set of n squared such that n is negative 2, negative 1, right? So let n take any of these values. N squared is an element of the set. So list the elements of the set. And then the set of n in the positive such that n is a factor of 24. So for each of these, you want to write down curly bracket and the list of elements of the set, closing curly bracket, right? Because, I mean, these things define the set, but they want to actually see the elements in there.
May we use ellipses if the set is extremely large?
If the set's extremely large and it's clear, yeah, you can use dot, dot, dot. All right, number 4, use set builder notation to describe the following sets. So here they're giving you a series of sets, and for each one of those they want you to write something like this. The set of all x such that, the set of all q contained in here such that. Right, so here you're given a set builder notation, list the elements. Here, question 4, they're listing the elements and they want you to describe it with set builder notation. So that's working with those definitions. And then section 1.2, I would like you to do number 4. And number 4 is asking you to show some of these equalities that we've just talked about. So give examples to illustrate the following facts. For example, A minus B is not the same as B minus A. Okay, how do you show that? Define a set A, show me the elements of it. Define a set B, show me the elements of it. Now calculate what A take away B is, right? If you've got to do some work, show the work. And then clearly indicate A minus B equals blah, right? And then show what B minus A is, show your work, and then write down clearly B minus A equals blah 2. And then simply state blah 1 is not equal to blah 2. Or in question part A, if A is a subset of B and B is a subset of C, then A is a subset of C. Give an example to prove that. Let A be the set blah blah blah, let B be the set blah blah blah, let C be the set blah blah blah. And then state for the reader, you know, A is a subset of B. And state for the reader B is a subset of C, and then state A is a subset of C. Right? So these things, when you do these, right, and you're working over the set of integers from 1 to 9, when you do these yourself, it'll be clear to you why these things are true, but you're trying to demonstrate it on paper, right? So the steps that you're going through in your head, you want to figure out what those are, right? And that's part of the key to doing these kinds of things, is being able to observe what you're doing that says, oh yeah, well obviously this is true, right? So go back and try to light bulb that moment, but notice what it is that's making it obvious. All right, and then question 6. is playing with complements. So suppose that you use an infinite universal set, so think integers or real numbers or something like that, and A and B are infinite subsets. Think about questions A, B, and C. Are those things true or not? And in question 8, we haven't really gone over the details yet, but go back and look at the text where it talks about subtraction and think about this. I'm not going to grade this one, and we'll talk about it in class on Friday or Monday. But play around with it, right? And there's some examples in this section of the text, but that won't be one that I'm grading. And then 1.3, number 2, so that's one using Cartesian products. So suppose you're about to flip a coin, roll a dice, let A be the set containing head, tail, B contains the integers 1 through 6. What's the, so when you have a set with bars on either side of it, that means how many elements are in there. Okay, so that's a definition. Type S means the number of things in S. But only if S is finite. So think about what A cross B means, what's the number of things in there, and how could you interpret that is something other than just a set. What's the meaning of A cross B? So play around with that and write a sentence or two. All right, and then you're done with homework 1. You're good for a week. So Friday I'll post up homework for next week, but we'll be working towards it. So Friday we will play with some more set operations and identities. We'll do story time. I'll tell you about Hilbert's Grand Hotel. We'll play around with infinities, and we'll dig deeper into this stuff and get to some non-obvious output. All right, have a good rest of the day, and I will see you next time.